In this video, we're going to talk about how we might actually graph a function of two variables, a function of x and y. There's an interesting challenge here, which is when we had single variable functions, so we're turning to that, a single variable input. What we obtained was a graph in the xy plane. There's one input, but we needed two dimensions to show everything because we were capturing the relationship between x and y with our function as the intermediary between those two variables. So we needed two dimensions, one dimension for the input and one dimension for the output. Well, that's going to get complicated then when we have functions of two variables, because we have two dimensions for the input and one for the output. So to draw these graphs of two input functions, of two variable functions, we're going to need three dimensions. And how does that work? We're going to have points in x, y, and z where we have our input as an xy pair, and the third dimension is going to be our output, a z value. For terminology, we call this three-dimensional space R3. And that just captures the idea that we have the real line in the x direction, the y direction, and the z direction. So we can go in any one of those directions and get points. We're going to continue to use the real lines as axes, have our same origin idea, just extended now to a third dimension. So what does it mean to graph a function like f of xy? Well, if we have a domain that's on the xy plane, then what we do is we can pick any point in the domain. So we go to some x coordinate and then out to some y coordinate. And then the function, f of xy, tells us what height we should be at that point. If we reproduce that process at collections of points in x and y and get the matching points in z, what we end up with is a surface. So imagine some sort of sheet of plastic that's being bent or manipulated into some shape that would define or is a good visualization for a surface. Another nice visualization is simply a hillside. Imagine yourself out in a park and you're positioned on the park and you look around, you can see the surface moving down or up around you. That is a good metaphor for the kinds of things we're going to be doing when we talk about functions of two variables. Now, how would we actually go about drawing this graph? Well, we're going to begin with our axes. The axes we pick when we're drawing them, unfortunately, in two dimensions, is typically done like this, where we have the x direction, imagining it out towards you, out of the page. But if we're drawing it on a two-dimensional page, we take this isometric perspective and imagine it coming out towards you at an angle like this. The y dimension is heading in the positive direction to your right, and the z positive direction is heading upwards. What we can then do is pick any xy point that we like and compute, based on those values, the height or the function value. If we calculate with our function and we get a positive z value, then that would be a point above the plane xy. If we get a negative value for z, then it would be down lower, it would be below the xy plane. Now, let's try a simple example. What if we had our function of x and y equals simply the number 5? Well, the way to interpret that is z equals 5 for any xy value. So we go out to some x, we go to some y, we go up, and we find the height is 5. And we do the same thing somewhere else. And we do this thing, if we keep doing that over and over again, what we're going to end up with is a plane. We can't show the whole thing because the plane would technically go out forever in every single direction, but we can sketch a representation of it, which would be this flat surface, all at height z equals 5. So if you're drawing it intercepting this axis here, it would be out parallel to the y, out parallel to the z-axis, and always height 5, so 5 steps up from the xy plane. Even with a simple example, you can already feel, I think, that there's some challenges in sketching functions of two variables. Let's imagine the similar surface, z equals -2, for all x's and y's. We would start with our axes again, and the x, y, and z directions. But this time, our z is -2, which means it would be down 2 steps below the plane. And so we would then get a plane again, but it would be drawn below the xy plane. Underground, if you like, if you want that metaphor of ground level being the plane that we're drawing with the axes. So this would be the graph of z equals -2. Well, let's take it up one more notch. Imagine our function of x and y is 1, so these are z values, these are heights, these are vertical up and down values, plus 1 if y is positive, and -1 if y is negative. And because x is not explicitly listed or not used in the calculation, it's going to be the same for all x values. So how does that work? If we draw our axes, and we talk about the x direction, y direction, and the z direction, again, these are the positive axes we sketch, then imagine we go out to x equals 3 and y equals 0. It's over here. If we plug that into this function here, we'd have -1 because our y is at or less than 0. So we would go down to here. So that would be one of the points on our graph. And in fact, no matter where we go along this line, as long as y stays 0, because we're not moving out to the right, then we would get -1 values. If we then move left, keep moving left, that would be -y values, and we'd stay at that same height. So what we have is this graph that's been moved down by 1. This is z equals -1 for all of our y values that are less than or equal to 0. It's a plane that's down by 1 and extends outwards to the left, outwards to the front and back as well, though we can't visualize those or draw those as easily. Where things change is if we go to the right, because if we're going to the right, then our y values are then positive, and we take a look at what that would be. We would be up at z equals 1, and we'd get a plane at that height if we kept going in that direction. So we'd have essentially like a stair step. We'd be coming along at height -1, and then as soon as we reach this barrier, we would jump up to height +1. Let me draw this a little bit differently here, so it accentuates the contrast. Here we have the plane at -1 because our y values are less than 0. And then as soon as our y values hit positive quantities, as soon as our y's reach larger than 0, then our z, our heights, jump up to +1. So we could label the z-axis here with the -1 and 1 values. Notice we have a dotted line along this axis because this little line here is actually not contained in the plane. It's all the points here, but not up to the boundary because of this greater than 0 element in the function. And once again, you can feel this is getting a little more complicated than we might like, and certainly more challenging to sketch in any reasonable way. So what do we do about that? Well, in practice, we typically try to use computer software to generate plots of these kinds of functions. And because you won't have access to computer software on tests or exams, what we would like you to do is focus on the patterns in those kinds of graphs, where we can predict the structure without necessarily being able to draw them by hand. We will not generally ask you to sketch surfaces. What we're going to do is ask you to be able to identify surfaces, or, as we'll see in later lectures, how to draw alternatives to these kinds of graphs that convey the same kind of information. For now, let's focus on the recognition side.